When we speak of light losing energy while climbing gravity, we are not describing a mechanical struggle in the ordinary sense, as though photons were tiny balls slowing down against a resisting medium. Rather, we are describing something far more subtle and profound, the way gravity reshapes the very structure of time and energy itself. To understand this, we must first abandon the comforting Newtonian intuition that space is a stage and light is merely an actor moving across it. In the relativistic view, space and time are not passive, they form a unified fabric called spacetime, and gravity is not a force acting within this fabric, but the curvature of the fabric itself. Now imagine a photon, a quantum of light emitted from the surface of a massive object such as a star. At the point of emission, it carries a certain energy. In quantum language, that energy is directly related to its frequency. We express this relationship as E stra h neutral, where E is the energy of the photon, H is Planck's constant, and nu is the frequency of the light. At the surface of a massive star, where gravitational potential is strong, the photon begins its journey upward. But upward here is not spatial in the classical sense. It is a movement toward weaker gravitational potential, toward regions where spacetime is less curved. As the photon ascends, something extraordinary happens. The curvature of spacetime causes the rhythm of time itself to change between the point of emission and the point of observation. A clock deeper in a gravitational field ticks more slowly compared to a clock far away from it. This effect is known as gravitational time dilation. Mathematically, for a non-rotating spherical mass, the time dilation between 2 points can be expressed using the Schwarzschild metric approximation. Draw on delta T a text far, on delta T a text near and left 1, Navrak 2 GM, RC2 right 1 2 tala. Here, G is the gravitational constant, M is the mass of the object, R is the radial distance from its center, and C is the speed of light. What this equation tells us is profound. Time itself runs more slowly closer to massive objects. Now consider what frequency truly means. Frequency is not an abstract number. It is literally a measure of how many wave cycles pass per unit of time. If time itself is stretched differently between two regions of space-time, then frequency must also change when observed from one region to another. Thus, when light climbs out of a gravitational field and reaches a distant observer, it appears to have a lower frequency. This shift is what we call gravitational redshift. We can express this relationship in a more direct form. Diode frac delta lambda lambda frac delta phi psi 2 phi. Here, lambda is the wavelength of light, and delta p high represents the difference in gravitational potential between the point of emission and the point of observation. The equation tells us that as gravitational potential increases, meaning we move away from a massive object, the wavelength increases, and an increase in wavelength corresponds to a shift toward the red end of the electromagnetic spectrum, hence the term redshift. But what does it truly mean to say the photon loses energy? It is not losing energy in the classical sense of friction or resistance. Instead, energy is being reinterpreted by different observers depending on their position in the gravitational field. For the observer far away, the photon appears less energetic because its frequency has decreased. A text observed our H anu a text observed thousand since anu a text observed anu text emitted. It follows that E a text observed, E text emitted, I yet no energy is destroyed. This is one of the most delicate points in general relativity. Energy is not globally absolute in curved space-time. Instead, it depends on the geometry of the observer's frame of reference. One may picture this as follows. The photon is not losing something in transit, but rather space-time itself is stretching the intervals of time over which the wave oscillates. The wave crests arrive more slowly, not because the photon has weakened, but because the structure of time between emission and observation has expanded. If I may offer a metaphor, imagine a melody played on a violin at the bottom of a deep gravitational valley. As the melody climbs out of the valley, it is not the violinist who changes the tune, but the valley itself that stretches the rhythm of the music. To a distant listener, the notes seem lower and more drawn out, though the original performance has not changed. Thus, gravitational redshift is not merely a property of light, it is a fingerprint of space-time curvature itself. It tells us that energy, time, and gravity are deeply intertwined, and that what we call light losing energy is in truth the universe revealing its geometric structure through the language of waves. To say that time itself runs differently in gravity is to touch one of the most unsettling and beautiful realizations in physics. It is the point where time stops being a universal background clock and becomes a living participant in the structure of the universe. Before Einstein, time was assumed to be absolute. Newton's silent assumption that every observer, no matter where they stood, shared the same ticking cosmic metronome, but gravity quietly breaks this illusion. It bends not only space, but the rhythm of time itself. Let us begin with the essential idea. In a gravitational field, clocks do not tick at the same rate depending on how deep they are in that field. A clock placed near a massive object runs more slowly compared to a clock far away from it. This phenomenon is called gravitational time dilation. And it is not a minor correction, it is a fundamental feature of reality. To express this mathematically, we turn to the Schwarzschild solution of general relativity, which describes spacetime outside a spherical mass. The relationship between proper time, d tau, time measured locally, and coordinate time, dt, time measured far away from gravity, is given by d tau dt puisque 1 infrask 2 gem arc2. Here, g is the gravitational constant, m is the mass creating the gravitational field, r is the radial distance from the center of that mass, and c is the speed of light. This equation contains a quiet but profound message. The square root term is always less than 1 when r is finite and close to a massive object. That means d tau lambda, no text emitted, is. This stretching of wavelength is what we identify as redshift. But let us go deeper into the meaning, because the mathematics alone is not the full story. What is truly happening is not that the photon is changing its internal clock, but that space-time itself provides different rates of time for different positions in the gravitational field. The photon is merely carrying a consistent oscillation, but the rulers of time used to measure it are not uniform. To understand this more intuitively, consider the gravitational potential, MPHI, defined in classical terms as phi isofrac gm IJ. In weak gravitational fields, the time dilation effect can be approximated as di tau haprox dt ha left 1 pasm fraction phi theta 2 are right. Since ampi is negative, the closer you are to the mass, the smaller that tau becomes compared to dt. Time is effectively slower, deeper in the gravitational well. Now imagine light being emitted from such a region. Every oscillation of the electromagnetic wave is tied to the ticking of local time. If local time is slower, then fewer oscillations are produced per unit of distant time. Thus, from the perspective of a distant observer, the light appears stretched out, not because the photon has changed, but because the time intervals defining its wave structure have been distorted by gravity. A useful way to summarize this is, locally, physics appears normal, and light is emitted with standard frequency. Distantly, the same process is measured against a different flow of time, producing a lower observed frequency. This is why gravitational redshift is inseparable from time dilation. They are not two separate effects, they are two faces of the same geometric truth. In a poetic sense, gravity does not simply pull matter downward, it slows the unfolding of time itself. The deeper you stand in a gravitational field, the more the universe seems to hesitate in its own becoming. And so when we say that time runs differently in gravity, we are not describing an illusion or measurement error. We are describing the fact that time is not a universal river flowing evenly for all observers, but a landscape shaped by mass and energy, where every step downward into gravity is also a step into slower time itself. To understand Einstein's equivalence principle at work in gravitational redshift, we must enter one of the most delicate and profound ideas in all of physics, the realization that a gravity and acceleration are not merely similar, they are locally indistinguishable. This statement sounds almost innocent, yet it dissolves the boundary between two concepts that were once considered entirely separate. And from this dissolving boundary, gravitational redshift emerges not as an isolated phenomenon, but as a necessary consequence of the geometry of reality. Let us begin with the core idea. Einstein imagined a simple but powerful scenario, a sealed elevator in deep space, far from any gravitational influence. Inside this elevator, an observer cannot see outside. Now, suppose the elevator is accelerating upward with a constant acceleration, a. The key question is, what does the observer inside experience? They feel a force pressing them to the floor. Objects dropped inside fall downward with acceleration, a. To them, it feels exactly like gravity. Now, Einstein's radical insight was this: no local experiment inside the elevator can distinguish between uniform acceleration and a uniform gravitational field. This is the equivalence principle, and it can be expressed conceptually as antext acceleration and nequiv antext gravitation locally. This is not a metaphor. It is a statement about physical equivalence in local frames. Now let us connect this to light. Imagine a beam of light is emitted from the floor of the accelerating elevator toward the ceiling. The elevator is accelerating upward with acceleration A. While the light is traveling upward, the ceiling is moving upward as well. By the time the light reaches the ceiling has gained velocity relative to the point of emission. This relative motion introduces a Doppler-like effect. In special relativity, the relativistic Doppler shift for small velocities, VHLC, can be approximated as dij I frac delta nu naprox frac vi free I. But in the accelerating elevator, the velocity is not constant. It grows with time. Over a height, h, the velocity difference can be approximated using di v approx ae and frac chi solos. Here, the time taken for light to traverse height, h, is approximately hc, since light moves at speed c. Substituting this into the Doppler shift expression gives sine one frac delta and nu and r nu naprox o frac a h c2 dians. This means the frequency of light measured at the top of the accelerating elevator is lower than at the bottom. Dar nu and chi text top. Whenever you see a gravitational redshift, you are also seeing acceleration written into the fabric of spacetime. And so, what appears at first as a property of light is actually a deeper statement about reality itself, that motion, gravity, and time are not separate phenomena, but different expressions of a single geometric truth. To see gravitational redshift as a cosmic proof hidden in starlight is to realize that the universe itself has become an experimenter, patient, vast, and brutally precise. It writes its conclusions not in ink or chalk, but in the stretching and compression of light that travels across unimaginable distances. Before Einstein's theory matured, starlight was considered mainly a messenger of composition and motion. We learned the elements of stars through spectroscopy, and we measured their velocities through ordinary Doppler shifts. But there remained a deeper question. Does gravity itself leave a fingerprint on light that cannot be explained by motion alone? Einstein's answer was yes, and nature eventually agreed. Let us begin with the simplest observational idea. When light escapes a gravitational field, its frequency changes. In weak gravitational fields, the fractional change in frequency is given by delta nu ran nu prime the frac delta for pi to down here, or delta nu is the change in frequency, r nu is the emitted frequency, or delta right pi is the difference in gravitational potential between emission and observation, and c is the speed of light. This equation, simple in appearance, becomes powerful when applied to real astrophysical objects. Consider a white dwarf star, a remnant core of a dead star. Its surface gravity is enormous compared to Earth's. A photon emitted from its surface must climb out of a deep gravitational well. The gravitational potential at the surface can be approximated as dal thas e phi saver frac gm r where g is the gravitational constant, m is the mass of the star, and r is its radius. When light escapes from such a compact object, the change in gravitational potential between the surface and distant space is essentially delta I phi frac gm by substituting this into the redshift relation gives frac delta anu phi as frac gem reach 2. This equation tells us something extraordinary. The more compact and massive the star, the stronger the redshift of its emitted light. Now let us interpret this not merely as mathematics, but as physical testimony. When astronomers observe spectral lines from a white dwarf, they expect certain frequencies based on laboratory measurements on Earth. Yet what they observe is a slight but measurable shift toward lower frequencies. This is not random noise. It is systematic, predictable, and consistent with the curvature of spacetime. To express the observed wavelength shifts, we use the relationship lambda for nu tal. Since the speed of light c remains constant, a decrease in frequency nu must correspond to an increase in wavelength and lambda. Therefore, I lambda, text observed, I lambda, I text emitted. This stretching of wavelength is the redshift signature imprinted by gravity itself, but the true beauty of this phenomenon lies in its universality. It is not limited to white dwarfs. It becomes even more dramatic near neutron stars, where mass is compressed into a radius of only about 10 kilometers. In such extreme conditions, the gravitational redshift becomes large enough that it significantly alters the observed spectrum. For very compact objects, relativistic corrections become essential. The full Schwarzschild redshift formula is data frac nu, a text observed, nu, a text emitted, chu rescort 1, and frac 2 GME ray 2. This square root factor encodes the full geometry of spacetime outside a spherical mass. As r approaches the Schwarzschild radius, I pi rs r star frac T2 gm, C2 tells the expression under the square root approaches 0 and the redshift becomes extreme. In the limiting case where r onto rs as we find r nu text observed by onto $0. This is the mathematical expression of an event horizon. Light escaping from such a region is infinitely redshifted and effectively disappears from observation. Now let us return to the cosmic proof aspect. Why is this so powerful? Because gravitational redshift is not an assumption. It is an observational consequence verified across many systems. Spectral lines from white dwarfs are redshifted exactly as predicted by frac delta nu frac gem e2. Precise measurements of atomic clocks on Earth at different altitudes confirm the weak field form. Frac delta nu the frac G HC2. Light near neutron stars shows strong relativistic shifts matching the full Schwarzschild expression. Each of these is a different scale of the same truth. Gravity reshapes time and time reshapes light. But perhaps the deepest insight is this. We are not merely observing distant stars. We are reading the geometry of spacetime itself through their light. Every photon arriving from a star carries within it a history, not just of where it was emitted, but of how time flowed along its journey. The equation E prime H nu I reminds us that frequency is energy, and thus gravitational redshift is also an energy transformation dictated by geometry. And yet no energy is mysteriously lost. Instead, energy is redistributed according to the gravitational structure of the universe. In general relativity, energy conservation is subtle. It is locally preserved but globally dependent on spacetime curvature. Thus, the universe is not merely a stage where stars shine. It is an active participant in the color of that light. In this sense, gravitational redshift is a cosmic proof because it shows that spacetime is curved, time is dynamic, and light is sensitive to geometry itself. When we observe a redshift in starlight, we are not just measuring distance or motion, we are witnessing the universe bending the very rhythm of electromagnetic waves across billions of years. And so the stars become philosophers in their own silent language, telling us that what we call color is not merely a property of light, but a dialogue between energy, gravity, and the structure of reality itself.